Okay, so my name is Tejas Gokhale. I'm an assistant professor at UMBC. And today I'm going to talk about the challenges with evaluation of text to image generators. Um, so before we get into the details of text to image generators and their evaluations, I wanted to point out that the connection between vision and language is really old, much older um, than we would like to believe it is. Especially in the machine learning community, we have formed this myopic um, outlook on, oh, vision and language is 10 years old or 15 years old or 20 years old. But really, it's a lot older than that. And humans, since ancient times, have used vision and language to communicate about the world and actions of humans in the world and their effects on the world, right? So many carvings and paintings and sculptures all over the world are, visual descriptions of what humans observed, and they are often accompanied by inscriptions. So these could be, uh, uh, symbols, or they could be language. And we still kind of use this, right? So we have children's picture books, we have comics, we have memes, and so on, which to this day we continue to use that connection between vision and language as a very fundamental form of communications. And so humans create stories in language to describe their experiences and visual observations. So humans learned to speak, but then one of the major functions of that speech, of that language, was to communicate what we saw, right? So one of the major functions of language is to express what we see and express it to others in a way that others can understand it. And in that process, we've developed a common understanding of uh, language where we assign sounds and meaning to objects that we see. So this is a dog, so the babies start calling it a dog because they observe other people calling it a dog. And we do this every day. And so we've been doing this perception and reasoning since the day we were born. We've been building uh, knowledge based on our visual experiences or based on what people teach us by designating names and properties to things that we experience. And so, in a nutshell, semantic vision is that subdiscipline within computer vision where we are interested in teaching computers to assign meaning to visual signals like images and videos. And that meaning usually comes in the form of natural language. So I like to think of vision as this pyramid, a hierarchy of sorts of tasks going from more physics-based tasks like understanding pixels and optics and geometry, but on top of that we start getting into semantics like assigning or designating meaning or names, image classification, object detection, and so on. And once we have that sort of designation, we can start using it for communication with humans, with machines. And on top of it is speculative vision. These are useful for reasoning about things beyond what is currently visible. And image generation from text is really a speculative visual task because we're using limited knowledge about the scene, usually in the form of sentence, and trying to generate entire images from it. And that really requires a lot of other capabilities, reasoning abilities, common sense, word knowledge, and so on in order to be accurate. So my group, the goal of our group is really to work on robust semantic vision. So teaching computers to assign meaning to visual signals with robustness and reliability. And we look at several aspects of robustness. We look at how language or meaning can have a positive impact on dealing with these aspects of robustness. And we also work on capabilities that can boost reliability. So that includes dealing with common sense or spatial and physical reasoning, and so on. So robustness and reliability is especially critical at this juncture, just the beginning of 2024, where we're beginning to see vision and language technology having a very big impact on our lives. And so as we see these technologies, as we see these uh, large scale models being adopted in day-to-day products, we must ensure that we are in a position to comment quantitatively about their reliability, about their robustness. Um, and so the goal of my work, therefore, has become very interdisciplinary. We, of course, work on the core areas of vision and language, core areas of visual recognition, and in doing so, we have adopted approaches from these different communities. More importantly, for today's topic, we'll focus on the evaluation and benchmarking art that we're trying to push forward. So we've, really led the community through various activities in this domain. So we have organized workshops on open domain reasoning and data engineering for robustness in multimodal settings. So today I'm going to talk about the challenges with evaluation of such, vision language models, specifically text-to-image generative models. And I'm going to show you why this really is a hard and challenging task by focusing on this particular case study where we look at spatial reasoning, so the ability of T2I text-to-image models to perform spatial reasoning. Right, so T2I models are part of a larger umbrella term called conditional image synthesis, and that has been quite an attractive research topic in vision and graphics because it allows a transformation from low-level information to photorealistic images. And so the goal is to train models to map structured inputs, so it could be layouts, scene graphs, sketches, language, and map that to the continuous image pixel domain, right? Um, the most user-friendly, the most human-friendly capability is generating images from text, right? Because humans communicate in language, and so this is the most obvious way for humans to use conditional image synthesis. T2I is a fairly new research topic, and I'm showing in this slide results from some of the earlier work here in 2016. And at that time, the community was very impressed that neural networks could learn this mapping between text and images. But we were aware that the quality of outputs wasn't great, right? It was very obvious that these images were artificial. There are so many artifacts, there's so much noise, and it's not photorealistic. The objects kind of look like the objects they're supposed to look like, but we know that these are fake images, right? Lots of distortions. And then barely 7 years later, or 6 years later, we've seen a paradigm shift, right? So just during 2022, in fact, there has been a substantial progress in terms of achieving high photorealism, exceptional high resolution images that are very hard to, it's very hard to say whether they are real or fake images. And especially zero shot capabilities, generating novel combinations and so on. So we're all very excited about the potential applications of these models, both in terms of research as well as the array of technologies and products in so many industries, including AI, just engineering, arts, media, and so on, even education, right? So there's a lot of potential for these models in products, but there's also a lot of potential for these models to solve problems in computer vision. So I'm going to briefly just give you a glimpse of two recent works that have come out. So one which uses T2I as a source of synthetic data. So T2I in combination with large language models. So the question is, can we use that synthetic data from LLMs and VLMs and T2I models to produce data to train computer vision models? It's a very interesting idea, but it's an old idea, right? So, can we use synthetic data to build robust models? Has been a long-standing question in vision. Turns out we might be in a position to say yes to that question, right? Still very preliminary results. There's also been the use of T2I models for data augmentation, right? So this is another very recent work where T2I models were used for data augmentation, right? So for the reliable use of T2I models as data generators or data augmenters, we will face some problems. The question is, have we faced these problems before, right? So the ML community or visual learning community has faced many problems with data fidelity in real data sets, right? So that can be, if you train your model using real data sets, there could be, adversarial attacks, label poisoning, mislabeled or unlabeled data, just data scarcity, domain shift. I mean, there could be so many problems, biases, and spurious correlations in data sets. So all of these problems have existed, even with real data sets. And we might be doomed to face the same problems with synthetic data sets. And we might be introducing newer problems. For example, how can we guarantee that the data that we're generating is correct, right? I mean, we might use some text prompt to generate an image, but once that image is generated, does it really match or align with the input that was used for generating it? Does it reflect what the intention was in creating that data? So there are many new problems that might arise. They could be just new formulations or new avatars of the same old problems, but that they could also be different reliability issues with synthetic data. And we therefore are at a juncture where we need reliable, holistic, comprehensive evaluation metrics and benchmarks so that we can really explore the utility of T2I models in vision. So the question is, how are T2I models evaluated today, right? So what are the existing evaluation metrics and protocols? And so how do we even evaluate whether a generated image is good, right? So let's look at an overview of existing metrics. So this is actually a bit dated. There have been a couple of other metrics that have come out, but this still reflects the overall kind of categorization of evaluation metrics in T2I models. The first category is purely visual metrics, right? So inception score and FID measure how photorealistic the images look. Do they look like real images, right? So it's a purely visual evaluation, and it doesn't consider the text prompt that was used for generating those images. The second category, the ones in green, this is the idea of image text matching or image text alignment, obtaining a score that represents how aligned the output image is with the input text. And there are different ways of doing this. There are some retrieval based methods. There's clip score, which uses clip, the vision language model, to produce a similarity score, or you can also use image captioning based metrics. And then the third way is to use objects. So focus on objects, figure out if we are generating objects that are mentioned in the text prompt, and forget about everything else, right? So an object-centric evaluation. And of course, you can have human study, right? So that's kind of blocked behind the box, but the fourth in gray is human studies, right? So humans are asked to rate the quality on a scale, quality of the generated image on a scale of 1 to 5, 1 to 10, whatever, or to just say if it's a fake image or a real image. Okay, so there's a lot of metrics, right? So are these metrics always effective? Can we evaluate complex reasoning abilities of T2I models with these evaluation metrics? So we look at this question with the case study of spatial relationships between objects. So I'll tell you why I'm talking about spatial relationships. So early on in my PhD, I had the opportunity to witness Alison Gopnik speak at CVPR 2019. So that was my first CVPR, where she spoke about her research on how babies as young as 1 year old acquire fundamental abilities of visual reasoning about sizes and shapes and geometry and spatial relationships and logic and so on, right? So even babies start thinking logically and spatially even before they learn to talk. So really, this is a fundamental ability that not just human babies, even mammals in general, or perhaps even broadly animals possess, right? And we use spatial relationships every single day. They're very intuitive, right? Dog above dog above table, dog below a table, chair to the right, to the left. So these positional or spatial relationships, left, right, above, below, are crucial in terms of how we understand and communicate about the visual world, right? And humans communicate using spatial relationships with one another, but more so these days also with robots, also with machines. So in the robotics community, there's a ever growing interest in using natural languages, English, Hindi, Japanese, to provide instructions to robots. And understanding spatial relationships is incredibly important to the success of these applications. For example, place the mug on the right of the box or open the left drawer, stand in front of the picture, right? So all of these instructions will only be accurately followed if the vision language model can understand these instructions. And these abilities are exactly the ones that we need in vision, because the abilities of spatial reasoning and logical reasoning are crucial for moving forward with embodied AI. So can existing metrics that we saw before quantify such spatial relationships? So let's look at some examples. Okay, so let's look at visual metrics like FID and inception score. These metrics, measure how close the images are to the real distribution of, photographs. But the text is never part of the evaluation process, right? So in this example, although the text says motorcycle to the left of an elephant or motorcycle to the right of the elephant, and even though in both cases the relationships generated are actually incorrect, FID and inception score are not going to measure that discrepancy, because they're only comparing the quality of the generated image with the distribution of real world photographs. So as long as you generate photorealistic images, FID and inception score will be high irrespective of the text. So essentially, we cannot use FID and inception score to measure spatial understanding of T2I models. What about object accuracy? Again, this SOA, for example, evaluates if a generated image contains objects that are mentioned in the input text. If all objects are generated, then the SOA is 100%. But if you look at these examples, both objects are generated in all four examples for truck to the left of cow, cow to the left of truck, blah, blah, blah. But in some cases, the spatial relationships are not correct, right? So even if SOA is 100%, it doesn't account for the wrongly depicted spatial relationships. So this metric cannot, measure spatial reasoning. What about clip score? So clip score is a recent T2I evaluation metric. So the idea is simple. You have a clip model which gives you a similarity between image and text. So you use it, you compute the similarity between the generated image X and the input prompt T. Now, what we did here was we flipped the text prompt. So a backpack below a train became backpack above a train. But then we measured the similarity of the same image with both T and T flipped and found that in a lot of cases, in fact, in majority of the cases, there is no measurable difference between clip score of X comma T and clip score of X comma T flipped. So for both below a train and above a train, the clip score is identical almost. And we saw this for at scale. And so we also looked at captioning based metrics, where again we use an image captioning model to generate a caption C for image X, and then compute the caption score between C and T flip, and measure the difference between these two. And for for both the caption based scores and clip score, what we found was that the difference, the delta between the original score and the flipped score was negligible, right? So basically these metrics are not able to distinguish between incorrect spatial relationships. So they will assign more or less the same score for a bicycle above a bench above a bicycle and a bench below a bicycle. These two sentences are exactly opposite, but the scores are identical. And that's not good. So we need to figure out if T2I models generate accurate spatial relationships, and clearly the existing metrics are not useful in this case. So we ran a large-scale study where we created an automated evaluation metric and a test data set. So here are some more examples of failures of, in this case, DALI V2. So our benchmark is called VISOR, short for Verifying Spatial Object Relationships. And this was a collaboration with Microsoft Research. So our contributions are a test dataset, SR2D, and an evaluation framework, VISOR, for benchmarking spatial relationships generated by T2I models. We've developed an automated evaluation framework called VISOR, which we'll talk about in detail. So let's talk about the dataset. So the dataset contains text inputs that describe spatial relationships between two objects, and these are created using a very simple template: object A, relationship R, and object B. So we chose 4 types of relationships, but it can be expanded to more. So a microwave sink and left becomes a microwave to the left of a sink. Elephant, cat, right becomes an elephant to the right of a cat. So these are simple phrases, simple sentences, where each object A and B is picked from the 80 different object categories in MS COCO. We chose MS COCO because it's a large-scale, real-world, object-centric vision language dataset. Okay, so some numbers. So we essentially have 80 choose 2, which is about 3,000 combinations of object pairs, and then 8 different relationships between them. So we get around 25,000 text prompts, right? So now we have text prompts that we can use to generate images, and that's exactly what we did. Okay, so to evaluate spatial understanding of T2I models, we created a metric called Visor. So Visor is a very simple idea. It's the percentage of examples for which the correct spatial relationship is generated, given that both objects are generated. So obviously this is a conditional metric. So it's conditioned on the fact that both objects A and B have been generated. And we did this for a reason. In the process of working on this project, we found that T2I models in general struggle with generating multiple objects if they're mentioned in the text prompt, right? So if you mention objects A and B in the text prompt, it's more likely that the model will only generate one of those. And so we wanted to disentangle the ability to generate multiple objects from the ability to generate spatial relationships correctly, right? So Visor essentially allows you to disentangle those two abilities. We'll also see other variants of Visor in the next slide, but this is really the crux of this work. Okay, so the definition of object accuracy is trivial. So given an Oracle object detector, object accuracy is 1 if both objects A and B are generated, and it's 0 otherwise. So even if you generate one of the two objects correctly, object accuracy is 0. Okay, and as I mentioned before, we also have a Visor unconditional definition where if rgen is the correct generated relationship and R is the ground truth relationship, then the unconditional Visor is essentially 1 if you have the correct relationship and both objects, and it's 0 otherwise, right? Okay, we also created a variant of Visor called Visor N. Here I'm going to use N equal to 4 as an example. A useful feature of T2I models is that you can generate multiple images for the same text prompt and then pick the one that best matches your needs as a user. So this is motivated from a usability perspective. And so Visor N reflects how good T2I models are at generating at least N spatially correct images for a given text prompt, right? So if you generate 10 images and you want at least 4 of them to be correct, Visor N gives you that accuracy. Okay, so we use an object detector. So this could be your favorite object detector. We've tried on DETR, we've tried open vocabulary, vision transformers, OWL-VIT. And what we do is we detect objects in the generated image, um, find the centroid of those objects, and then based on a very simple rule based on the centroids of both objects, we convert those centroids into a predicate, which basically says A above B, A to the left of B, and so on. And then we compare that with the ground truth, which is given in the input sentence itself. So in this example, the input is a motorcycle to the left of an elephant. So we know that the relationship is left motorcycle comma elephant, and then we generate the image and then find the predicate from the generated image and compare it with the true ground truth predicate, right? Okay, so in a nutshell, state-of-the-art T2I generators lack spatial understanding. So what we found is like even sophisticated models like DALI v2 or Stable Diffusion are not really great at generating spatial relationships. So they do have attribute level compositionality, which has been shown, in the popular avocado chair examples or many other popular examples. But when it comes to spatial compositionality, there's still a large struggle. Okay, so here are the detailed results. The columns show object accuracy, and then all variants of the visor metric. So there's unconditional, conditional, and then visor n for n equal to 1 to 4. So as you can see, DALI v2 actually has the highest object accuracy, but it doesn't have the highest conditional visor, right? So because we've disentangled object accuracy with spatial reasoning, we can actually begin to see the differences between these models. So it turns out that CogView2, which is an older model, is actually better at generating spatial relationships, but it's pretty bad at generating multiple objects, right? So its its object accuracy is only 18%, whereas DALI has an object accuracy of almost 64%. So this is an interesting thing that we've discovered as part of this project. And it's important to take a look at the unconditional column. So this actually tells you that if you took 100 prompts and ran all of these models, the best score that you get here is like 38% from DALI. So which means that if you generated 100, if you generated images for 100 prompts, only 38% of the times will you get accurate spatial relationships and both objects. So this actually reveals how hard it is to do spatial reasoning, and even the conditional variant is the highest performance is only 66%. So this table really reveals how challenging a problem spatial reasoning with T2I models is. So T2I models tend to merge objects sometimes. So cow to the right of a donut. There's a cow shaped thing, but it's like a pattern on the donut, a bench below a keyboard. Now this looks like a bench, but it's actually a keyboard, so you can sit on it, but it's not two different objects. Laptop to the left of a cat. Okay, the cat is like on the screen of the laptop, and so these merging, this merging phenomenon is quite interesting, and it makes evaluation difficult because now you can detect both objects using an object detector, but how do you say that this is an accurate generation when there's actually only one real physical object? So T2I models also struggle with word sense disambiguation. So here I'm using the example of the word mouse. So mouse in different contexts could mean the animal mouse or like the keyboard mouse. So what we did was we compared qualitatively different models. So a skateboard below a mouse is a prompt that we've used in this example, and you can see that DALI Mini actually doesn't at all generate a mouse. CogView and DALI V2 tend to generate computer mouse, and Stable Diffusion has the animal mouse. And again, in some cases, there's the merging problem where the mouse is basically a design or a pattern on the skateboard. We also found that T2I models are biased towards commonly occurring, commonly co-occurring object pairs. So basically, you might imagine, chairs and tables are more co-occurring, laptops and mouse are more co-occurring, people and cars probably or bicycles are more co-occurring, but uh, like a car and a microwave is probably not that common in data sets of real images, right? So what we saw was that the visor scores were higher for commonly co-occurring supercategories, so COCO supercategories, and lower for unlikely combinations like indoor-outdoor objects, like vehicle and appliance or electronic and outdoor. So this was at the supercategory level, but we did this as a fine-grained study and found that there's a correlation between object co-occurrence in MS COCO and visor scores. So essentially, if a pair of objects has a higher likelihood of co-occurrence in a MS COCO image, then the visor score is likelier is likely to be higher, right? So basically it shows that if you have co-occurring objects in real life, or at least in the real world data sets, um, wiser scores for T2I models will be higher for those pairs, but lower for unlikely object pairs. And one of the key um, use cases for T2I models is that we should be able to use them to generate unlikely or out of distribution or atypical objects together, right? So that really is the potential of T2I models to solve the data scarcity problem, right? If I want to generate cars with microwaves, I should be able to do that. But it turns out that there's a correlation between object co-occurrence in COCO and the ability of models to generate these objects. And so we're stuck in the loop again where the dataset statistics from COCO are essentially dictating the success of T2I models. And we've done the study on COCO, but uh, because it's a good representative dataset, but we're confident that the same trends will exist in larger datasets like Lion and so on. Now, there are other biases and inconsistencies. So there's a text order bias. So object accuracy for the first mentioned object in the text is significantly higher than the second object. So basically, if I mention two objects in a sentence, it's more likely that only the first one will be generated, which is not ideal because we want both objects to be generated. Um, There's inconsistency between equivalent phrases, so merely rephrasing the input can have a large influence on the spatial correctness of the output. So, for example, a cat to the left of a dog, the Weiser scores for those kinds of sentences versus dog to the right of a cat, which is equivalent, but you see a difference between the Weiser scores for these two. So you can simply rephrase, make an equivalent rephrasing of the sentence, and you can get differing results or outputs. Similarly, you can have linguistic variations of the prompt. So you can say like a phrase, or you can make it a sentence, like there is a cat to the left of a dog, or you can split the sentence. You can say a cat to the left, dog to the right, or a cat to the left and a dog to the right. Or you can say there is a cat to the left, period, there is a cat to the right. So by doing these kinds of variations, again, we see that these lead to different outputs for all T2I models. And so merely rephrasing the input seems like it has a large influence on the spatial correctness of the output. So we may need to do some prompt engineering, but if we want these models to be reliable, it's not very clear what kind of prompt engineering is going to work. So in order to get some insights, we did a small scale controlled experiment where we added sizes and color attributes to our sentences. So instead of A, R, B, so object A to the left of object B, we said, so as an example, a large black cat to the right of a small brown dog. So instead of a cat to the right of a dog, we added these modifiers, right? And so we added different combinations of these size and color attributes on both objects. And we saw that overall addition of the color attribute resulted in a drop in spatial understanding of T2I models, but addition of size descriptors improved the performance a bit, right? So there are some trends like these which exist, but it's not very clear how we can improve the performance of T2I models by simply doing prompt engineering. And it's my hunch that that's not the final solution. I'm going to end this presentation by talking about broader implications of these modifiers or concept compositions, because concept compositions are hard. So here's an example from Gautami. So she was trying out, WhatsApp stickers. So so she tried sad and tired Indian girl working on a laptop without headphones. Now, again, this is another set of kind of modifiers to the nouns in the sentence, and this is, I think, from WhatsApp. So basically, it's unable to generate all of those objects together, or it's generating some attributes but not others. So concept composition is hard. Um, and is there a way for users to be aware of this? Well, the obvious answer is holistic benchmarking, but uh, even that's a hard problem. So it's just an evaluation should be easy. Just collect a data set and pump out some numbers is not going to be the solution, and we will need some very controlled setups or um, grounded evaluation techniques, yeah, in order to move forward. One such technique or one such benchmark that we'll talk about later in this tutorial is is concept bed, where we are evaluating such concept learning abilities. Um, but I want to end with kind of a glimpse about how Visor has been adopted in recent work as a benchmark for evaluating new T2I models, or fine-tuned T2I models for different reasoning abilities within a very short span. So our data set, our metric, our code is all available publicly, and I invite you to use it whenever you come up with any new T2I model. So to summarize, evaluation of generative models is challenging, and downstream effects on computer vision models are unclear. I talked about the use of T2I models as data generators, but T2I models are already being used to create images, and they are being uploaded to the internet. Um, this could lead to data poisoning for vision models that are trained on internet data, and we might not even know why uh, we have failures. The failures could be inscrutable because we no longer would have control over which images are real or fake, or which images are correct, which images are poisoned, and so on. Um, uh, from a different perspective, end user experience is very anecdotal. So whenever a new T2I model is released, it's released with cherry picked examples saying, here's what you can do with these models. But it turns out that for your specific use case, you're not guaranteed that it's going to work, right? But if I told you that I'm going to release this new Microsoft PowerPoint product, but if you use like a font size of less than 10, we don't really know if it's going to work, right? I mean, that's going to be frustrating if someone releases a product like that. We're at that stage with T2I models, but with um, good evaluation protocols, with comprehensive benchmarking, whatever that means, we'll get there, right? So, and reasoning abilities are going to be crucial because humans do a lot of reasoning, and humans are going to use these technologies, but they are hard to evaluate. Um, so, as a take-home message, the take-home message is that holistic benchmarking is critical, it's important, it's needed, but we have a long way to go in order to actually, come up with a very comprehensive benchmark. So that's some of the work that we are actively doing in my lab. So I am hiring PhD students. So if you're applying for the fall or 24 or 25 cycles, send me an email. I'm broadly interested in working on perception and reasoning models that are robust and reliable. So that's the punchline of my group. And I'll also be talking about uh, some of my work along the broader goal at the AAAI new faculty highlights talk. So I have run over my allotted time by more than 10 minutes. And so I'll stop and thank all of my collaborators, and thank you very much.